The topic for today is essentially all the cool and interesting things we can have with a radio telescope with multiple antennas. It is session 5 beamforming here, and we will see how beamforming works. And I will also speak a bit about interferometry. You might have already seen images which are made with antenna arrays, and maybe you've had some introduction about how those are made. So hopefully we can gain some more intuition. This is the last session. Next week, we will be at the Allen Telescope Array, which is an array of 42 antennas. So with this session, you will have a better understanding about how it works and why arrays of many small antennas are quite popular these days in radio astronomy. So let's go ahead. I have GNU Radio Companion here. The flow graphs I'm going to use are already on GitHub. I think I can open them. Yes, they are. So on beamforming, there is beamforming demo and beamformer array demo. The first one I'm going to work on is beamforming demo, but I'm going to put it together from scratch so that I can explain how everything works. So let's see, I'm going to simulate a signal which is supposed to come from a source on the sky. We can think of an astronomical source, any kind of transmitter. It might be a natural phenomenon, or it might be an artificial transmitter, might even be a spacecraft. It doesn't really matter. So we are going to simulate that signal, and we are going to simulate a receiver with two different antennas. I'm using just two antennas because it's simplest. If we understand how two antennas work, then we can scale it up with many more antennas. And the next flow graph will actually have 6 antennas, I think. So this is a simulation. I can use any sample rate I want. For simplicity, I'm going to use 1 megasample per second, which means 1 million samples per second. And that means my bandwidth is 1 megahertz. And I'm going to generate the signal of interest that we intend to receive. And I'm going to generate it with a noise source and a polyphase arbitrary resampler. So we have already seen that approach. I recall that a noise source is going to generate noise. And if we want the bandwidth of this noise to be smaller than the total bandwidth we have in here, we can put a polyphase arbitrary resampler and set a resampling rate which is greater than 1 and corresponds to the ratios of frequencies. So I'm going to control things with GUI entries because I want to be able to interactively play around with this and to show how different parameters affect the output. So I'm going to put it at a certain frequency defined here in hertz, maybe 0 by default. It's going to have a certain bandwidth. I'm going to set it to 100 kilohertz. And this part of the flow graph, since it's something that we have already seen, it is quite good as a refresher. So the resampling rate needs to be the sample rate divided by the bandwidth of the signal, wideband bandwidth. We are basically interpolating by 10 with this particular choice of parameters, which makes sense because the bandwidth of this is going to be 100 kilohertz, but we need to get up to the sample rate, which is 10 times more. And then the rest of the parameters I can leave as they are by default. Something else I want to do is I want to have the ability of shifting this signal in frequency. That is the reason I have added this wideband frequency. And then I'm going to do that with a signal source and multiplying. So you might remember that there are a number of different ways for how to shift the signal in frequency. One of them is to multiply with a complex exponential or complex cosine, as in here. And I should put here wideband frequency. And then what else? I need a throttle block because this is a simulation and I want it to run in real time. And for the time being, I can put here a frequency sync so that we can look at the waveform and see that it is generated correctly. What else? Yes, I also want to be able to set the signal to noise ratio. And sorry, I want another one of these. So this is going to be wideband SNR. Here it should say wideband signal. Wideband signal SNR. And now there is a formula here, and I'm actually looking on another window at the finished flow graph so as not to make mistakes. And I'm going to write it and explain it. It's very similar to some of the formulas we have seen already. Let me see, divided by sample rate, divided by wideband bandwidth, like so. And I need to close parentheses properly. So let me see, do I need an additional parentheses? No, the problem is that numpy is not defined, but I think I have the right number of parentheses. Okay, so let's import numpy. And then I can go back to this formula. So what do we have in the formula? We have 10 to the power wideband SNR divided by 10. That is just converting from decibels to a linear scale. Then we have the sample rate divided by the wideband bandwidth, which is basically the same resampling rate we have setting here. And that makes sense because this division is the sample rate at which the this noise source is going to run. So then this is the noise bandwidth for this noise source. And for example, if I want this to be 10 times stronger than the noise, then I would say this is 10 to the power 10 divided by 10, which is basically 10. You know that 10 decibels is the same as a factor of 10 divided by the noise bandwidth. And that makes the signal be 10 times stronger than the noise. I haven't added the noise yet because each of the receivers is going to have its own receiver noise. We have two antennas, so we will have like two virtual receivers, and we will simulate the receiver noise in each of them, but it's going to have amplitude 1. So that's the reason that we have here the bandwidth. Anyhow, not too important how to set the SNR appropriately. What else do I need to do? I need to give this a name, so beamforming demo 2, and this is going to be beamforming demo. And then I think I have everything I need to save. And now I have everything to run. So as you can see, I have a signal which is 100 kilohertz wide. It goes basically from minus 50 kilohertz to plus 50 kilohertz. And at the moment, there is no noise. When we simulate the receivers, there will be a noise floor, maybe over here. We can check that all of this works. So we can put 200, for example, and now it's twice as wide. We can put 100,000 here. And now it's centered on 100,000 hertz, so 0.1 megahertz. And we can make these 10 times larger, so now it's almost as minus 40. If we increase it by 10, it's now at around minus 30. And we can also try minus 10, and it works. So now it's at minus 50. So everything makes sense, and I think nothing here is new. Any questions about this? Okay, sorry. Let me see. Yeah. The next thing is going to be more interesting because we are going to simulate two receivers receiving this signal, and then we will beamform them, which means we will combine the signals from the two antennas. So I'm going to use something which I think I have explained, but I haven't used frequently, which is a virtual sync. A virtual sync is used to do connections rather than drawing a line connecting to blocks. You put a line into a virtual sync, and then you have a virtual source, which is the other end of the connection. And I'm going to call this here astro signal for astronomical signal. I need to put the same name here. And these two are now connected. And the reason I'm using virtual sources is because since I want to have two receivers, then I can copy and paste and put one receiver here, put another receiver here, and it will be quite tidy. Otherwise, I would need to run a connection from here to the first receiver, another to the second receiver, and I would have lines everywhere. So what happens with the receiver? The receiver adds some additional things to the signal. They are often called impairments because they are things which modify the signal, usually in a way which is more difficult or more inconvenient to receive. The first of them is the receiver noise. We have spoken about it just from the beginning, from the moment we plugged in the RTL-SDR to the computer, we saw that any kind of radio receiver is always generating some noise. So these receivers are going to generate noise. And that's going to become important for beamforming. Another thing which happens is that the signal which is transmitted from an object in space, you need to imagine it as it is traveling towards our radio observatory, and it will reach both of the receivers, but usually it will not reach them at the same time because you can think about the antennas, they are in different positions on the ground, and the signal will come from one particular direction. Let's say it's coming directly from the south for simplicity. So if one of the two antennas is more towards the south than the other one, then the signal will reach the southern antenna first, and it will reach the northern antenna later. So what happens is basically the propagation length or the time of flight, which is the time that the signal takes to travel from the transmitter to the receiver, is different for each of the two antennas. And we can also simulate that with GNU Radio. What else is going to happen? The other thing is that is going to happen is that not only there is a difference in the time of arrival of the signal, this thing I was speaking about, the signal is coming from the south maybe, and one antenna is uh, more towards the south, so the signal arrives first. That's called time difference of arrival because that's what it is. It's the difference in time uh, when the signal arrives to each of the antennas. But what is also going to happen is that this time difference of arrival is going to be changing all the time because the Earth rotates or the apparent position of the object changes on the sky. You can imagine if the previous example, if the object is exactly on the south, looking from the observatory, and we have one antenna on the south, one antenna on the north, then since the Earth rotates, the object is apparently moving to the west on the sky. And as it rotates, then it will change the time difference of arrival. Another example, which I think is better, is if you imagine the two antennas on an east-west baseline. That means the two of them has the same latitude, but one of them is on a more easterly longitude than the other one. Then we can think of what happens with any source on the sky. It will rise on the east, and then when it rises on the east, the eastern antenna will be closer, so the signal will arrive closer, will arrive sooner to the eastern antenna. Then the object will keep moving on the sky throughout the day. It will transit. That means it is exactly on the south, as seen from the observatory. And when that happens, since the two antennas have the same latitude, the wavefront will arrive simultaneously to both antennas. So now the time difference of arrival is 0. And as the day moves on, the object will go into the western part of the sky and finally set. And while this is happening, the signal will arrive sooner to the western antenna. So we have seen how this time difference of arrival changes sign over the course of the day, because if we compute it as east minus west, it is positive at the beginning and negative at the end. And it is 0 when the source is transiting. So the time difference of arrival is constantly changing. And something you need to keep in mind always about radio frequency is that phase and frequency are related. Frequency is the time derivative of phase. And because we have a time difference of arrival, we also have a phase difference of arrival. Because phase changes over time, you can think of the signal propagating through space. And if you are in different points of space, you are going to see different phases. At different points in time, you are also going to see different phases. So basically, the fact that the signal arrives at different times to each of the two antennas also causes a different phase in each of the two antennas. And I'm saying that the phase difference changes over time continuously. So that actually means that there is a time frequency, there is a frequency difference of arrival between the two antennas. One of the two antennas will see a slightly larger Doppler effect than the other one because they are not in exactly the same place on Earth. And the Doppler effect, because of the Earth rotation, depends on the longitude and latitude of the receiver. So this was a mouthful of explaining everything. It will probably be more clear once I put a plugin here that can do all of this. But before doing that, any questions about what I just said?
Sorry, could you explain again how the frequency changes for the two receivers?
Yes. So do you believe that the phase is different for the two receivers because the time of arrival is different?
Yeah, that makes sense.
Okay. And this difference in phase, we can compute it. We can think of plotting it, for example. And as time changes, it will change its value because the Earth is rotating. Okay?
Oh, okay. Yeah.
So then if you take the derivative of that function, you have plotted it, and you can take the derivative. The derivative is going to be the derivative of phase difference. So it's going to be frequency difference, just because the time derivative of phase is frequency. And now you have something which is non-zero because it's changing, and it's actually changing. So because the phase difference is not linear, it has a sinusoidal shape. So we will see the derivative. It also has a sinusoidal shape, and that's the frequency difference of arrival.
That makes a lot more sense. Thank you.
Okay, great. Any other questions? Great. So there's something called channel model in GNU Radio. And you can see there's channel model. There is also channel model 2, and there is a whole category of channel models. And channel means anything that happens between a transmitter and a receiver. Here we are thinking about radio observatories, but in the real world, much more complicated things happen. You can think of your cell phone. It might be inside your pocket. You are inside a building. The cell phone tower might be somewhere in another building, and the signal is going to bounce on many objects, buildings, trees, whatever. It's going to enter through a window or maybe through a wall, and it's finally going to reach the cell phone on your pocket. So that is a wave propagation problem, which is really hard to simulate. And there are models for how, like simplified models for how this wave propagation works. And if you are working in cell phone communications, you can think that That can be quite important to try to predict how good the signal is that your cell phone in the pocket is receiving or how distorted it is. We have a much simpler situation because there is very little between the transmitter and our receiver. It is just empty space. And yeah, to be honest, there is the interstellar medium, but we're not going to be talking about that now. The only thing we're going to be talking is about the fact that the two antennas are not in the same place, so the signal arrives at a slightly different time to each of them. So channel model, this is the basic one. It can simulate noise. Perfect. That's something we want. We want to be able to simulate the receiver noise. It can simulate a frequency offset. That's also great because we wanted to simulate that frequency difference of arrival. We wanted to simulate that the Doppler effect as seen by each of the two antennas is slightly different because of this whole thing about phase difference of arrival changing over time. There is a parameter called epsilon, which I think it's better explained here. It tells the sample timing offset to emulate the different rates between the sample clocks of the transmitter and receiver. 1.0 is no difference. So that is how it's usually used in communications because the transmitter and receiver clocks will be slightly different. No clock is perfect, but we are going to use it to simulate the fact that the delay between the two antennas is changing over time. Because this is epsilon, it's what it does essentially is it's introducing a delay which is continuously changing over time. It's delay rate. It's the time derivative of delay that is +1 actually. That is how you need to think about it. It will be slightly more clear when I put the formula in here. And finally, there is tabs, and I don't know what's about tabs in the documentation. Yeah, it says tabs of an FIR filter to emulate a multipath delay profile. So multipath means when the signal reaches the antenna through multiple paths. That's the cell phone in a pocket situation. I was mentioning the signal might arrive through different paths by bouncing off different objects and buildings. And then you will see multiple copies of the signal arriving, each of them with a different delay. And that's what the tabs in here are intended for. But we can use them to simulate the phase shift or the phase difference between the two receivers. So that is the way in which we are going to use the tabs here, just for the phase difference of arrival. So we will only use one tab. We can add more tabs, and so for example, I don't know, we could have tabs like this, and this means there is a signal, which is the signal multiplied by 1, and it arrives with a delay of 0. With a delay of 1 sample, the same signal multiplied by -1 arrives 2, and with a delay of 2 samples, the same signal multiplied by 3 arrives. So that's how you do multipath. But for this tutorial, we are going to do no multipath, so just the phase difference. What else? There is something very important, which is the seed. The seed, it is a random seed. It is used to generate the noise. And you can see that this noise source also has a seed. By default, the seed is 0. But very importantly, I want each of the noise sources in the flow graph to be generating different noise, more precisely to be generating independent or uncorrelated noise, because otherwise nothing will work and it will not be a good representation of the real world. In the real world, if we have two receivers, the receiver noise on each of them is uncorrelated. It is statistically independent because it's generated by different electronics on different receivers. They are physically separated. So the bottom line is we need to use different seeds, and the number doesn't matter as long as they are different. So I'm going to put 1 here. And I'm going to duplicate the channel model, put it on the second receiver. And what I'm going to do is, because we only care about the difference between the two receivers, we only care about the difference in frequency. For example, we only care about the difference in delay rate. We only care about the difference in phase. Then I'm going to leave all of these as it is with the default values, which basically means add no frequency offset, add no sampling rate offset, which is how epsilon is often called. Do not change the phase of the signal. And I'm going to add all the effects to receiver number 2, which is this one. That doesn't matter. I could add half of the frequency difference to each of them. I could put everything on receiver number 1. It doesn't really matter for the kind of simulation we are going to use. So with that said, I'm going to go to the second receiver. I'm going to choose a different seed, very important. So I need seed number 2, seed number 1, seed number 0. All the seeds are different now. And then, well, something else I forgot to do was to put the noise voltage to 1. So I said before at the beginning when I was explaining this formula that the receivers will have a noise amplitude of 1. So this is where I set it. But now let's think of the formulas we need in here. And to do that, I actually need some entries to define the parameters I'm going to use. So I'm going to put them maybe here. It's a good place. So phase difference. Let's see. In general, there is going to be a phase difference between the two receivers because the antennas are not in the same place, and we are going to enter it manually. There is also going to be a frequency difference because the Doppler effect is going to be slightly different. Frequency difference in hertz. The difference is usually going to be pretty small. It's going to be a fraction of a hertz, but nevertheless, it is there and it actually matters. What else? There is going to be a delay rate difference. So as I was saying, the delay, the time difference of arrival, is generally not going to be 0 and it's going to be changing over time. So that's what we mean by delay rate difference. And I'm noticing that I also want to add a delay. So we want to have a delay difference as well. And then this is going to be in samples. And this one, the units, some units that I like are parts per million. That means that, for example, if the difference is 1 parts per million, in a million seconds, the delay will have grown to 1 second. Since we are not going to be waiting for a million seconds, it is easier to think that in 1 second, the delay is going to increase by 1 microsecond. So that is what delay rate of 1 ppm means. And so that you have some numbers about distance in your head, 1 microsecond is the same as 300 meters or about 1,000 feet. So for example, if the antennas are separated by 300 meters or about 1,000 feet, which is more or less the largest separation of antennas on the Allen telescope array, then for some particular orientations of the transmitter on the sky, basically when it's on the same line as the two antennas, the difference in times of arrival will be 1 microsecond. So that should hopefully make some sense now. And the question is, how do we add this delay? This block doesn't support the delay. So we need to use a delay block. I think I haven't explained this block, but it's actually really simple. It just adds a delay. It makes things appear on the output however many samples we tell it here. So this is how we simulated delay difference. For the rest of them, I'm going to write the formulas and then we can discuss if there are any questions. So let's see the frequency offset. We always need to look at the documentation to see what are the units And this is somewhat confusing in this documentation because it says the frequency offset is normalized to the symbol rate. So for example, it says 0.25 would be 1/4 of the symbol rate. The good way to think about it is that it's normalized to the sample rate. So if we have the frequency difference in hertz, and we also have the sample rate in hertz, then we need to divide. And now we have basically a frequency offset in cycles per sample, which is the result of this division. The epsilon, it is quite easy. So it is actually 1.0 plus the delay rate difference. But the only thing is this is in parts per million. So I need to multiply by 10 to the power minus 6 so that it is in parts per 1. So for example, 1 ppm here will give me 1.000, bunch of zeros, 1. Or in another way, 1 plus 10 to the power minus 6. And then finally, the phase difference. So the taps are complex numbers. They are multiplied by the signal. And then I can use NumPy to convert from degrees because I have set the phase difference to be in degrees. That is easier to reason about than radians. So we can convert here. And these are all the formulas we need. Any questions about these formulas or anything we have covered so far?
Could you, I just can't like see it from here. Could you maybe explain it again? Like the equation and the taps, what it is?
Yeah, but is the font size too small? I don't know if I
Yeah,
can.
it's a bit too small.
Yeah, I don't know if I can make it larger. I think I can make the window larger, but the font size is going to be the same. But I
That's
can,
good.
okay, I can go through the formulas again.
Okay.
And hopefully that will be clear. So for the frequency offset, I divide the frequency difference by the sample rate because this is supposed to be entered in cycles per sample. And then I have hertz in here and samples per second. So hertz is cycles per second. And so the dimensional analysis of this formula gives me cycles per sample, which is what I want. Then epsilon, as I explained, the easiest way to think about it is that it is 1 plus the delay rate in units of parts per 1. And because I have the delay rate set in units of part per million, I need to scale it down to part per 1. And to do that, I multiply by 10 to the power minus 6. And finally, in the tabs, I just want the complex phasor, which when multiplied by the signal is rotating the phase by this phase difference, which is in degrees. And then such complex phasor is complex exponential of 1j multiplied by the phase, but the phase needs to be in radians. So we use NumPy to convert from degrees to radians. Does that make sense?
Yeah.
Okay, great. Any other questions?
Yeah, I was just wondering if you have more than two receivers, like how would you find like the phase difference then? Like would you just do it all relative to one receiver or yeah?
Yeah, we can do it relative to one receiver because only the difference between each pairs of receivers matter for the problem. And this is just for simulation to keep things simple. But when conducting real observations, it is quite common to choose a reference antenna. And then you pretend that everything is perfect for that antenna. And you figure out what are the phases and delays on all the other antennas with respect to your reference antenna as part of the calibration process. So this approach of saying one antenna has everything set like to default values or nominal or perfect, however you want to call it, and the rest is what is going to be different or what I'm going to change is a quite common way of thinking. Other questions?
I guess just a comment on choosing a reference antenna. So, there's various ways of doing that, but you might want to choose one if you're looking at an array that has sort of a lot of antennas in the core and then more sparse antennas further out. You probably want to pick one that's closer to the core rather than picking one that's then going to kind of have more effect from any offsets there.
Yep. Okay, so let's move on with this. And what I'm going to do now is I want to beamform. Beamforming is basically adding the two signals together. They are complex numbers. And the whole point of doing the simulation is that we will be able to see what happens when we just add these two signals and they have different phases or different frequencies or even different delays. We will be able to see the effects. In a real beamformer, what needs to happen is we have these real world effects from propagation, so time difference of arrival, etc. And before adding the two antennas together, we need to compensate for those effects. We need to calibrate, we need to have a model for how the propagation is going to be, which is basically where the antennas are located on the ground, coordinates for each of the antennas, where the source is located on the sky, so coordinates, right ascension and declination for the source. And based on that, we can figure out what are the geometric delays, as they are called. And then there are also going to be instrumental effects, which need to be calibrated out, because I haven't spoken about cables and electronics so far, but for most of these, not for the frequency really, but for all the other things in which delay is important, you can think that the cables also matter, because if the cable run from the first antenna to the receiver is different from the cable run of the second antenna to the receiver, then there is also going to be an additional delay on the cables, which is going to be different. So that also needs to be taken into account. And the delay through a cable depends on the temperature of that cable. It depends on the frequency. Also the atmosphere, so the delay through the atmosphere can depend on weather, and it can be different for each of the antennas. So all of these effects, which are non-repeatable, they need to be calibrated out. And I will explain how to do that later. So in this simulation, basically, we are asking ourselves what happens if we don't calibrate these quantities, which is relevant even in a real observation, because no calibration that we do is going to be perfect. So there will always be some residual error. And then we can have an understanding about how that residual error affects the beamforming. So what I'm going to do is to put 3 inputs in here so that we can look at each of the individual antennas and then the sum of the two antennas. Antenna 1, antenna 2, and then beamformer, which is antenna 1 plus 2. And before moving on, I'm going to stress somewhat more what are we trying to do here, because I said we are going to beamform because we have 2 antennas, but maybe I didn't say what's one of the main reasons for beamforming. So you can think about the size of your antenna, the physical size of the dish, as a collecting area. The larger your antenna, the more signal power you are able to collect. And it is clear that if we are trying to receive weak signals, then the larger the antenna, the better, because we have more collecting area. So we can receive more power. And basically, going back to the simulation, we will increase the SNR of the signal and we will make it easier to see. But sometimes we have several antennas which are small, and then we would like to somehow combine the signals received by all of the antennas so as to effectively add all the power collected by each of the antennas. It is the same as forming a virtual antenna which has a collecting surface, which is the sum of all the surfaces. And that is one of the reasons we can beamform we can perform this addition. And if everything is set correctly, and that means if all the things here have been calibrated out so that it is actually the same signal arriving to both receivers after calibration, then we will add, and you can think 1 + 1 = 2. I will go back to this 1 + 1 = 2, but basically after this addition, the signal is going to be twice as large or n times as large if we have n antennas. And when I go back to this calculation about how the SNR increases, it will be more clear why it increases, but for the time being, you can believe me that we are summing the power on all of the antennas by doing this. So that is a reason. There are other reasons, which we will see after the break, but one main reason is increase the SNR, accumulate power over all the antennas. And this said, let's see how all this looks like. I think I want to set this wideband SNR to something like 10, because otherwise it will be very difficult to see anything. And maybe I want to set something like a low averaging here. Okay, and now we can see something. And what we see is the signal which is arriving to antenna 1 and antenna 2 is pretty much the same. You can see it has the same power. It's not literally the same, and I can freeze this plot so that you can actually see it better. So you can see the noise is different, but that is just because in each of the receivers, the receiver noise is different. We set different seeds to achieve that. So no surprises about that. Antenna 1 and antenna 2, they are receiving the same signal. The receivers have different noise. When we add the two signals together, then we get a larger signal. And the signal should be twice as large because we are basically adding the same thing twice. And twice as large means 3 dB. And maybe there is a bunch of noise in this plot, but maybe it is more or less clear. So this is minus 33.5, and this is minus, yeah, I said something wrong. So twice as much in amplitude is 6 decibels. You need to be careful, and I need to be careful too, when thinking about amplitude or thinking about power. 2 times the amplitude is 4 times the power, which is the same as 6 decibels. So there should be a 6 decibels difference between the single antenna and the sum of the two antennas. And let's see if that's the case. As I said, minus 33.5, more or less, minus 27.5. And that's right, there is a 6 dB difference between minus 27.5 and minus 33.5. So the math works out. But then what happens with the noise? We can see that the noise is actually larger on the sum of the antennas. And if we measure, it is, I don't know, minus 41, minus 44 should come out here. It is noisy, so it's difficult to measure. And maybe with more averaging, it can be clearer. Let me see if I can do more averaging here. Yeah, maybe like this is clearer. Minus 41 point, I don't know, 0.5, minus 44.5. So it should be more or less clear that there is a 3 dB difference between the noise level. And why is that? Well, the reason is we are adding also the noise from the two receivers, but the noise is uncorrelated. And because it is uncorrelated, then when we sum, we are summing two normal random variables. And the result of adding two independent normal random variables is a normal variable with square root times as much standard deviation, because the variance adds, but the standard deviation doesn't add. It comes with a square root. So we basically have square root times as much noise in amplitude, and square root in decibels, when we are speaking about amplitude, is 3 decibels of amplitude. So that's why we only get a 3 dB increase in the noise. And then that means we are winning SNR because the signal has increased in 6 decibels, but the noise has only increased in 3 decibels. So overall, there's an increase in 3 decibels of SNR. And that should make sense because no matter what we do, we have 2 antennas. They are supposed to be equal, so the same collecting area. When we combine the power of the signal collected in both antennas, we expect the power to go up by a factor of 2. We expect the SNR to grow by a factor of 2 or 3 decibels. So no matter what we do, then the SNR needs to grow by 3 decibels. And I'm putting some stress in this because adding the antennas is a simple thing to do, but there are some people who choose to normalize. So we could divide by the number of antennas after adding, which is the same as calculating an average over all the antennas, or we could divide by the square root of the number of the antennas such that the noise floor doesn't move, it stays at the same level. It depends on what we want to achieve and how we want to normalize things. But no matter what we do, the SNR is going to grow by 3 decibels. Any questions about SNR?
I have a question. I want to understand a little bit more about the behavior of the signals. So are we expecting that the blue and the red signals are kind of the same ones and we're just adding them so we can kind of make rid of the noise that is there? Or it's more like they are slightly different and we are adding them kind of to get a more completed signal that we can study?
Okay, good question. Let's do all of this, but without the noise. Let's do it with just the signal, and maybe it will be more clear. So to do it without the noise, I put 0 in here, and I put 0 in here, and then what we can see, I'm going to put stop, is the 2 signals on the antennas are identical. Now we can no longer see the difference. It's basically the same data on the plot. I'm enabling and disabling this antenna 2 so that we can see that antenna 1 is behind the red curve on the plot. So it's the same signal. And when we add together the same signal 2 times, so that's the addition here, we have exactly the same signal, we get 2 times the signal. And if we compare any point in here with the point below, it should be exactly a difference of 3 decibels because this is basically the same number multiplied by 2. And we are, sorry, 6 decibels. And we are multiplying the amplitude by 2 just by adding 2 things which are equal. I could also plot this in the time domain and it will be clear that we are multiplying the amplitude by 2. Is that clear what happens to the signal?
Yes.
Okay, great. Now what happens to the noise? Because we can divide this problem into the 2 ingredients. For that, I'm going to multiply this by 0. And then none of these matters because this is all zeros. The only things that matter are I'm generating a random Gaussian variable here of standard deviation 1. I'm generating a different and independent and correlated Gaussian random variable of the same standard deviation 1 in here, and I'm adding them. And then if you go into a textbook or something, what you will see is that, let me put some more averaging. You will see that the result of adding these 2 random variables is also Gaussian, and the standard deviation grows by a factor of square root of 2. And let me stop this. So we can now see the noise on each of the 2 receivers is different. We can see the curves are completely different. That is because we use different seeds because this is what we want to simulate. Each receiver has different noise. And they have the same power on average because we have put the same noise voltage in here. When we add them, we get something which is also random. It is Gaussian, and the amplitude is square root of 2 times as much as the amplitude in here, or in decibels, 3 decibels more, which is what we get in here. And I could also show it in the time domain. In this case, because everything is random, it's even more difficult to see things clearly in the time domain. But this is what happens with Gaussian noise. And then finally, if we have both the signal and noise, it's just the two effects combined. So wherever in the spectrum there is only noise, we see what we saw before. The noise grows by 3 decibels because of how the Gaussian variables are combined when summing them. And the signal goes by 6 decibels because we are summing the same signal. We have slightly different things in here, but that's the noise. So in the region occupied by the signal, there is also noise, the same as here, but it is much weaker than the signal.
Makes sense. Thank
Okay,
you.
great. Any other questions?
I have a couple of comments. I guess one is that you may also be familiar with this if you're thinking about integration time. You know, that if you integrate for longer, then your signal, you know, twice as long, your signal is multiplied by 2 and your noise is multiplied by square root of 2. And so your signal to noise is going up as the square root of your integration time. Similarly with bandwidth, if you have a wideband signal and you increase your bandwidth, you're getting more of that signal. You're just adding more signal in, but you're also adding more noise. And because of the central limit theorem, the noise is just going up by square root. And then I guess one other comment, you know, regarding your point, Valeria, about the, you know, the signal's the same coming from the antennas. One thing that we haven't talked about, but that those of you working on radio projects are familiar with is radio frequency interference. And some of that's going to be local to the individual antennas. The antennas might not behave the same. They might be picking up different RFI. And one advantage of doing beamforming as well is that if you're combining these different signals from a whole bunch of antennas, then the RFI should average down and the signal should pop out of the noise more.
So have we kind of been just going over like incoherent like beamforming or like
There's no phase delay
Yeah.
yet, right?
Well, I think we
And
have one of them.
It's delay 0.
Yeah.
Yeah.
This is coherent beamforming. This is coherent beamforming, yes. I haven't spoken about incoherent beamforming. Incoherent beamforming would be about summing powers. So we would need to convert these to power somehow. We have complex numbers in here, so we still have the phase.
Yeah,
And
okay.
then the SNR increase would be not 3 decibels, but 1.5 decibels because you have the square root of 2 losses.
Okay.
So yeah, there's only going to be coherent beamforming for today, but incoherent beamforming is also an interesting and important topic. Okay, so now that we have everything in place, what we can do is to experiment with these to see what happens when the signal that arrives at each of the antennas is not the same, because real world effects, or even if we try to do a calibration to remove these real world effects, the calibration is never going to be completely accurate. So what happens? How does affect that? How does that affect the beamforming output? And the easiest one to reason about is the phase difference. For example, what we can see is if the phase difference is 0, then both things add together, they combine constructively. And that is great. If I start to increase the phase difference, maybe I'm going to put this on low. At 45 degrees, it might not be so clear, but I start to get a small decrease in the amplitude of the beamformed signal, because now the two signals don't line up perfectly. They are at 45 degrees phase difference. If I increase this further to 90 degrees, then you can see that I'm not gaining much by beamforming. And I can keep increasing this further. I think at 120, I basically gain nothing. Well, I'm actually losing because the power of the signal is the same, but the power of the noise has still increased by 3 dB. And I think at 90 degrees error, we have the same SNR before and after beamforming, but that's not something you need to remember because this is a very large phase error. If you have a phase error of 90 degrees, then there is something completely wrong in the calibration system. And if we go even further and we go to 180 degrees, then the signal completely disappears. And that makes sense because 180 degrees phase difference means opposite sign. It means the signal is the same, but the sign is opposite. So when we sum, they cancel out. We get 0. It is destructive interference. And Steve was speaking about interference. We might have interference coming in from some directions which are different from the source. There is a technique which I'm not going to be simulating today, but I'm just going to mention now, which is called null forming. Null forming can be combined with beamforming, but the goal of null forming is to make a combination with the antennas in such a way that in the directions of the interference, we get cancellation. And so we can remove completely or by a large amount the interference. Of course, if we have many interference signals coming in from many directions, it's going to be very difficult or impossible to do it. But if we just have one, then it's totally possible to place a null so that any signal coming in from that direction disappears. So that is another interesting thing we can do with multiple antennas. So that's what happens with the phase difference. What happens with the frequency difference? It's pretty much the same thing, but changing over time. So for example, I'm going to set the frequency difference of 0.1 Hertz. And that means the phase is going to do one rotation every 10 seconds. And we will see the thing I was showing repeating in time every 10 seconds. So you can see the signal is decreasing. Now it increases. And it does one of these cycles every 10 seconds. So it is at 0 degrees phase difference. Now it is close to 180. Now it's close to 0 again, and it keeps repeating. So that's how a frequency difference looks like. And then finally, let me show a delay difference. But to do that, I'm going to increase the signal bandwidth because it will be clearer in this way. Let's put maybe 500, even 800, so that it almost occupies everything. So this is my signal, and I'm going to say what happens if I put a delay difference of one sample. And we can see that in some parts of the spectrum, there is cancellation. In others, there is not. If I put 2 samples, then I get cancellation here and here. If I put, I don't know, 4 samples, I would expect 4 notches. Maybe one of them is outside. If I do 8, it doesn't need to go by powers of 2, but I'm just doing that to demonstrate my point. I have 1, 2, 3, 4, 5, 6, and if I count on all the spectrum, there should be a total of 8. What is happening? The thing that is happening is that a delay is the same as a linear phase slope over time. And so, over frequency. We will see that in more detail in a second. But because there is a delay difference at some of the frequencies, there is going to be a phase difference of 180 degrees in this one in particular, and I will get cancellation. In some of the other frequencies, there is going to be a phase difference of 0, and I will get constructive interference. The signals will combine, they will add. And basically my phase difference is changing over frequency, and it is basically 180, 0, 180, 0, and that is what causes this interference pattern over frequency. Okay, questions about this? The next thing, yeah, go ahead.
With like, I've been struggling to try and edit the actual like variables at the top. I don't know if there's like a certain setting on the cells that you have to do in order to be able to edit them when you're looking at the graph, but like I don't know if I am like loading it up wrong, but I can't like manually input values while the graph is showing.
That is very strange. I've never seen that kind of bug. I guess there is a bug. You don't need to do anything to make these fields editable. The whole point is they are always editable, and you say you cannot write. So even if you just press the number 1, it doesn't type anything.
Yeah, like if I press the execute flow graph and I like pull it up, then it just is like I can't click on it to edit. But like I have the graph, but I just can't like mess with it.
Okay, I see. So you cannot even click on one of the fields to select it and start typing. You can see that when I click, it
Is it not execute graph? Is it like a different function to pull it up? Cause I don't.
no, it's execute graph. I think you are doing everything correctly, but somehow there is a bug with your system. I suggest we look at that next week because I will be in person and I can see it with my own eyes and it will be easier to fix. But that's a weird bug. I've never seen something like that. Yes, you should be able to click on these, and when you click, you will get the cursor. They will have some indication that this is the selected field, and you should be able to type things.
Okay,
So yeah, I don't know. Sorry.
no worries.
Any other questions? Okay, so the next thing I want to explain before the break is calibration and also something about correlation, because I said that if we have a real world beamformer, we need to correct for these effects. So for example, because of the propagation delay, the signal might actually be coming with a delay difference of 8 samples. And I'm going to set this exactly at 8 because this needs to be an integer actually, because of how this delay block is supposed to have to work, not because of any other reason. So then the question is, how do we figure out that the delay difference is actually 8 samples, or however, how we measure these quantities? Because part of the effects, we can compute them, they are geometric effects, and we can have a mathematical model for them. The other ones we need to measure in calibration because they depend on weather and electronics and all sorts of things. So how do we measure these? And a way to measure those is with something known as a correlator, which is going to compare the signals received at all the antennas, in our case at the 2 antennas. We usually point the calibrator at a calibration source. We will see what properties a calibration source needs to have at the Allen telescope array, but you can imagine it needs to be bright enough, it needs to be a point source, because otherwise we get additional effects that affect the calibration process. So that said, I'm going to show you how a correlator works. And maybe to save some time, I'm going to open this and copy and paste part of the flow graph, which is the final part, and then explain. And I'm going to connect it like this and like this. So I'm connecting each of these to the signals received by each of the antennas. And then I need an NFFT. Where do I have it? NFFT. So I'm going to do FFTs. And I also need a scale in here. Where did my scale go? Here. What is wrong here? Oh, I also need an integration time variable. So there we go. I don't know where it got pasted. Somewhere I have a variable which says integration time 0.1 second. I don't know where I pasted it, but luckily there is something which is the variable editor. And we can go in here and see that the integration time is 0.1 second. And this is used in this formula. So what is this correlator doing? If you have heard anything about correlators, maybe you have heard the term FX correlator. This is an FX correlator. It means that first it goes to the frequency domain using FFTs, and then it multiplies. And that is what it's doing. It's doing an FFT to go to the frequency domain. The number of FFT points is 256, which in this case, it is more than enough. I don't want to go into details of how we choose the FFT size. It depends on the maximum delay we need to compensate for after correlation. It also depends on how smooth the passband is, etc., etc. So there are reasons to choose a larger or smaller FFT, as well as computational complexity.
I'm gonna ask about correlators. I've been hearing the word thrown around a lot, and when I look on diagrams that show a correlator, it looks like a mixer and such, but I understand that the function of what it's doing to the signals is different. What is the actual function of the correlator does to different signals coming in?
It is a multiplication. It is this multiplication. A multiplication of usually of the one signal times the complex conjugate of the other one.
Okay.
That is why it's drawn as a mixer, because a mixer is a multiplication. We have used it in here, so this is a mixer as well, and it is a multiplication sign. Maybe the question is, why would we multiply to do a correlation? That might be a reasonable question. So
just use a mixer if we're doing because we need the imaginary component in there as well, or what is the?
Yeah, you can do all of these with real signals. So these days it is more common to use IQ signals, even in radio telescopes, not only in this simulation. But I don't know, maybe 40 years ago or in the past, I would just say real signals were more common, and you can have a correlator with real signals as well. The only thing that happens is if you have complex signals, you need to use the complex conjugate of one of them. If you have real signals, then it's just a real multiplication. So I guess the question, what I should explain is, why would we want to multiply two signals in the first place? And the reason for doing that is, you can imagine if you have any sort of signal, it is going to have positive and negative values. So if you integrate it, if you sum it up for a certain interval of time, then on average it's going to cancel out, because the positive going parts and the negative going parts average out. Now, if you have the same signal on two receivers, or two copies of the same signal, and there might be other signals, there might be noise as well, which are different in the two receivers. And then you basically overlay them on top of each other so that the signal, which is the same, is aligned in time. And you multiply. On the positive going parts, you are multiplying positive by positive. And so the result is positive. On the negative going parts, you are multiplying negative by negative. And so it is positive again. And basically, because of this multiplication, you have a bunch of positive numbers, whereas before multiplication, you have positive and negative numbers. And so when you sum, then you have a net result, which is positive. So said in another way, by doing this multiplication, and the complex conjugate is not so important here, by doing this multiplication, we achieve something that when there is a common signal in the two receivers will give us a positive result. And when there are no common signals, it will give something very small, because the average is supposed to be 0. Does that make sense?
Mm-hmm. Thank you.
Okay.
Makes sense a little bit. I have to chew on it more.
Yeah, this is something that needs to be internalize in someone's mind, but those are the things you need to think about what happens when you have a common signal if you multiply it, etc., etc. And the only fancy thing we have in here is the FFT, because we want to do a correlation in each frequency channel. That is how it's usually done. But we could multiply before and then do an FFT. That's another technique, which is called XF. So, okay, we do FFTs to channelize into different frequency channels. We multiply in each of the frequency channels the signal from the first receiver by the complex conjugate of the second receiver. And finally, the thing we do is we sum for an integration time. And I have set this as 0.1 seconds, and the formula is the usual one. And finally, I'm going to plot two things, and it will be easier to understand when we see the plots. But the things I'm plotting are the phase, which is extracted with complex 2 argument. This is just the phase in radians. And then I'm doing an FFT, and I'm plotting the magnitude. And importantly, this is an inverse FFT. These were forward FFTs, and this is an inverse FFT. So let's see how this works, and it will be easier to see why. So we have the simple situation in which the signal is the same on the two receivers. And we can see that in the center part of the phase, this is the phase of the correlation, we have 0. The rest is noise, and it's changing all the time because we are correlating this noise, and we get 0. I don't have a plot for the amplitude. I could add a plot for the amplitude here, but if I added it, we could see that the correlation amplitude is very small here, and it is larger here. But I'm more concerned about the phase. Also, what else? In here, maybe auto scale, we can see that there is a peak. It is on the two edges, and the reason is we need to think about this plot as this edge is glued to this one. So this delay, it says 256 samples. It also needs to be interpreted as -1 sample, -2 samples, etc., etc. So this is supposed to be periodic. I want to make this wider as before. I think I had 800 kilohertz. And now we can see that the phase is 0 in here. What happens is if I have a phase which is, I don't know, 45 degrees, will I be able to see it? Yes, I'm getting 45 degrees. There is something happening about the sign. Yep, there is a sign convention because I'm adding 45 degrees to the second signal, which is the one which has the complex conjugate. And that is the reason we get a negative sign in here, but it doesn't matter. So we can measure the phase difference in the correlation as we are seeing. Can we measure the delay difference? Well, we also can, because we can measure phase and we can measure it over frequency. So when the delay difference is 1 sample, we see that there is 1 full wrap of phase over the whole frequency span. And the reason I have the IFFT in here is because it's not so easy to see with 1 sample, but now this has jumped to a delay of -1 sample. I'm going to put 10 in here, and then we see 10 wraps. We count them, there are 10. And in the IFFT, we can see that the position of the peak is 245, which is -10. Or maybe 246, I don't know, it should be 246. Yeah, 246, which is -10, because there are 256 FFT bins. And as I said, this is negative because of sign conventions that do not really matter. So this is how with a correlator we can measure the delay difference between the antennas, the phase difference, and also the frequency difference. Just for fun, I'm going to put a 0.1 delay rate between the antennas, and we can see this thing changing smoothly over time, and the peak is shifting, and this is simulating that the time difference of arrival is changing over time because the source is moving on the sky, or it is apparently moving on the sky from the perspective of the observatory. I'm going to speed this up a little bit more. So you can see this is the kind of thing we can see in a correlator, and if we don't compensate for the source movement, we get this effect, which is known as fringe rotation. We see that the delay is changing over time, and we can see it in a number of ways. So, okay, let me stop this. Any questions about this? This is the end of this part, and we will break for 5 minutes and then resume with the second part.
I want to
So-
get better.
The next thing I want to show is something which is called a linear array. And this is a diagram of a linear array. It's called a linear array because we have all the antennas placed on a line. This is actually going to be two-dimensional. So it's a simple model for an array of antennas. And we are also going to assume that the distance between all the antennas is the same as in this diagram. So basically we have a line where we place antennas with a spacing which is d units of distance. And then what you can see on the diagram is that depending on the angle with which array from a distant transmitter reaches the array, then we will have a situation like this. So for example, this ray is going to arrive first to this antenna number 1, and then antenna number 2 is going to have an additional delay, which corresponds to this length, which is calculated here as d cos theta, where theta is this angle. And what happens with ray number 3? It has this additional propagation distance, which is 2 times d cos theta. And this one has 3 times d cos theta. And you can imagine what happens if we add more antennas. And in fact, the flow graph I will show in a second has 6 antennas. So it has another one here and another one here with delays. What was that? 4d cos theta and 5d cos theta. So hopefully everything is clear from the diagram. It's just trigonometry. The only small comment I want to make is that it is easier for me to measure the angle of arrival, not from here, but rather from the vertical. So I will be measuring this angle over there, the complementary. So rather than having d cos theta, I will have d sine of theta, and 2d sine theta, 3d sine theta, etc. That's the only difference. Any questions about this diagram? Okay, so we want to do a simulation of this in GNU Radio, and I have the beamformer array demo, which is already in GitHub. I think I committed it with 400 wavelengths antenna separation. I'm going to start with 100 and then bump it up to 400 to show the difference. So if you're running the same on your machine, just know that you might have 400 in here. I'm going to simulate 2 different signals. We already know how to generate them. It's the same thing as in the previous flow graph. I have the SNR frequencies and bandwidths for each of them. And the reason I want to have 2 signals is because I'm going to simulate that I have 2 signals coming from 2 different sources in 2 different directions, so that then I can see how each of them is received by the array. So we have astronomical signal 1, astronomical signal 2. The next thing is all the antennas. And what happens is at antenna number 1, the astronomical signal 1 gets a phase shift, which is going to be 0. And the astronomical signal 2 gets a phase which is supposed to be 0. But why is it 0? It's 0 because the formula, full formula, let me see if I can show it like this. Yes. So the full formula is basically what we had in the diagram I was showing before. We have the signal angle. We need to compute the sine of the signal angle. And because the signal angle is in radians, in degrees, we convert it to radians. And then when we have the sine of the signal angle, we need to multiply by the antenna separation. That was the d on the diagram. And because this is a phase shift in radians, we also need to multiply by 2 pi. And this is the first antenna, so it gets a 0 multiplied. We can go back to the diagram. So the first antenna is kind of the reference in here. It doesn't have any additional phase delay. The second antenna is going to have a phase delay of d sine of theta. So does it have it? If we go to antenna number 2, then on the same thing, it says still phase shift is 0, but that is just because, oops, sorry, by default, my signal angle is 0. But the formula, you can see it's 1 multiplied by 2 pi antenna separation, which is the sine of the signal angle, and so on and so forth. On antenna 3, we have 2 times 2 pi d sine of signal angle, etc., etc. What else do we have? We have astronomical signal 2. It's the same thing, but in the formula, we have the signal angle 2. So I'm simulating different angles of arrival for each of the two signals. We will be able to separate them and to see how we can use beamforming for that. And we also have the receiver noise. So a Gaussian noise source with an amplitude of 1, and it's going to have a different seed in each of the receivers. So seed of 0, seed of 1, seed of 2. To be absolutely correct, I should use different seeds. Yeah, I have different seeds. So I have here seed 100 and seed 101, so that I don't repeat any of the seed of these antennas. And the two astronomical signals phase shifted to account for this additional propagation delay, plus the receiver noise get added. And this thing here is what gets received by the first antenna. By the second antenna, third antenna, fourth antenna, fifth antenna, sixth antenna. As I said, these are 6 antennas to already have something which is somewhat interesting to see. And there's no way I'm going to be copying and pasting all of this in real time. You can imagine it took a bit of time to copy and paste all of this. So a nice thing about a beamformer is that it is a digital thing. It's just calculations done on a computer or an FPGA or a GPU. And because they are calculations as opposed to some analog RF hardware where you have dedicated hardware resources, we can have multiple beamformers working on the same signal. And we can have multiple beams pointing in different directions. So coming back to this diagram, we might want to point one beam to this direction to be able to receive this signal. And we might want to point a beam to another different direction to receive another signal, which is from a different direction. Or as some of you might have seen on SETI RF searches, sometimes we point a beam to the intended SETI target, and we point the beam to no targets, so to some area of the sky where there are no planets. And then if we see a signal in these two beams, then it's probably R5. If we see a signal only on the target beam, then it's likely to be a signal which is coming from the target direction. So having multiple beams can be used to receive different signals from different directions, or to find out if a signal actually comes from the direction we assume it to be coming. So how do we beamform? To beamform, we need to do the opposite phase shift. We need to align all these signals back so that when we add them, they coherently sum up. And that's the reason this is going to be for the first beamformer, this is going to be for the second beamformer. So for the first beamformer, I have a formula which is very similar to the one before, but it has a minus sign. We have a minus sign because we are correcting. And rather than signal angle, I have beamforming angle. And 0 because this is the first antenna. We can see the formula for the second beamformer. It is the same, but beamforming angle 2. These are all variables we can set on the GUI. And then the same thing here. So -1 times same formula, beamforming angle, etc., etc. And -2, etc. So all these connections, which they get added here, this is the first beamformer. I'm adding the 6 signals from the 6 antennas after the appropriate phase shift. And I'm on the second beamformer, I'm adding the signals from all the antennas after the phase shift. Maybe something else to mention is because in the first simulation, we were also considering delays. For simplicity in this simulation, I'm not doing delays. In general, we would also need to correct for those delays, either in the frequency domain or in the time domain. But I'm just considering phase shifts or phase delays for simplicity here, because that's the most important ingredient of a beamformer. The delay or group delay can be explained as a different phase delay on each frequency and can be done in the frequency domain. So once you understand this, you understand everything else. And finally, what I'm doing is I'm plotting the spectrum of these two. So I'm going to disable this for now. And before running any questions about the flow graph, maybe I'm going to zoom out so we can see the whole picture and see that it's rather large, but not so complicated. I don't know, this may be too small. But hopefully you get an idea of the structure. We have 6 different antennas, which we can see in here. Each of them receives 2 signals. They have different phase delays. We are correcting for the phase delay corresponding to 2 particular directions, and we are adding the 6 signals in 2 different additions, and these are 2 different outputs. Questions, comments?
I guess one comment here, you know, we're maybe thinking of these as sort of individual dipoles, like the antennas that you got with your GNU Radio hardware, and there are particularly low frequency arrays that use this technology, so you're not actually steering anything except you're using the delays to steer in the direction that you want to point. But some of you are also working with Meerkat. You'll be working with the ATA next week, where you also want to physically move the dish as well in the direction of interest, and or conversely, I guess, for that beam to be somewhere within the primary field of view of those antennas.
Yeah, that's a great comment, and that will appear in a second. For this demo, we are going to assume these are dipoles like this, and they, or omnidirectional antennas, they receive things from any direction. But with a dish antenna, we would also need to simulate the primary beam of the antenna. We will need to physically point the antenna to the source, and this will become relevant in a second. So yeah, let's run this and see how things look like. So at the moment, the 2 signals, we can see the parameters here. Signal 1, I think this is the one here because it's at 50 kilohertz. Signal 2, it is the one on the left at -150 kilohertz. They are coming in from the same direction, so they have angle 0 degrees, and our 2 beamformers have beamforming angle 0. So they are generating the same output because they are doing the same calculations. But let's take beamformer number 2, for example, which is the red one, and let's change it slightly by 0.1 degrees. We can start to see a small difference. What I'm doing is I'm pointing this beam away from the 2 signals, and then you can see that it is decreasing in amplitude. And as I keep increasing, then I'm going to do 0.1. At 0.1, I have already lost the signal. Maybe do 0.08. So on 0.08, the signal is very small. This is because the beam of my beamformer, which we will take a look at how it looks like in a second, already has a decreased gain for 80 millidegrees. And if I go to 100 millidegrees, which is the same as 0.1 degrees, I'm already on a null of my synthetic beam, so I completely lose the signal. Why is this useful? Because, for example, what happens is the signal number 2 is actually coming from that direction. Then we see that we have two signals. They are separated on the sky by 0.1 degrees. There's one coming from 0 degrees, the other one coming from 0.1 degrees. And by pointing each of the beamformers to the appropriate direction, we can separate the two signals. You can see the blue signal is on the first beamformer output, the red signal is on the second beamformer output. And this is also true if the signals overlap in frequency. In this case, I have signals which do not overlap in frequency, so thinking about separating them is somewhat unnecessary because we can already separate them by frequency. But you can also think what happens if they overlap in frequency. So for example, I might move this one to 50. Then if they came from the same direction, I would have no way of separating them because they are together. There is no way to pull them apart. But because they come from different directions and because I have an array of antennas, I can beamform and I can really separate them and have each of them on the corresponding beamformer output. So that is another reason why a beamformer is useful. Questions about all of this?
When you say same direction, how close in that direction does it need to be? Do they need to be like right on top of each other, or if it's 1 degree apart, it's going to be completely fine, or what is for them to be observed on top of each other like this?
Great question. It depends on the geometry of the array. So in particular, it depends on this antenna separation, which is the quantity d, and it also, because this is in wavelengths, it depends on the observing frequency. The antennas are going to be usually fixed on the ground. They will be, I don't know, 100 meters apart or whatever. And depending on your observing frequency, 100 meters might be 100 wavelengths, 1,000 wavelengths, 10,000 wavelengths, or whatever. So it depends on that, and it depends on the number of antennas. To answer that question better, I'm going to go ahead with this one and show you how it looks like. But for this particular beamformer, you can see that if they are at least 0.1 degrees of separation, we can separate them perfectly. This is for this particular choice, and I can give some formulas when we look at this. This is the antenna pattern, which will make things clearer. Before that, any other questions? Okay, so to understand beamforming better and to answer this question about how separated the signals need to be, what I would want to do is to look at, for example, let's say beamformer 1, which is fixed at an angle of 0. And then let's pretend I start moving the signal and I start recording how much amplitude I get for each of the signal's directions. And I could do this by hand, but it is terribly time consuming. But this is the quantity I want to look at. This is important, right? Because it tells me what is the response of the beamformer, how much signal I will see depending on the angle of arrival of the signal. So this is what we want to compute. And there is a formula. It's basically what GNU Radio is doing for all these calculations. I'm going to show how I'm computing this so that you see that there is nothing magic, and I'm showing it in GNU Radio because it's fun. Usually I would just plot it in a Jupyter notebook or something. So I'm considering all directions of arrival between -3 degrees and 3 degrees. I'm doing 2 to the 16 points between -3 degrees and 3 degrees. I'm choosing 3 degrees as, I don't know, some limit. As Steve was mentioning before, if we have a dish antenna, it's going to have a beam, so it's not going to receive signals in all directions. So maybe it has a beam width of 3 degrees, although that is rather large beam width for typical dishes and frequencies. And then if our dish has a beam width of 3 degrees, anything that happens outside of 3 degrees will not matter for us because each of the dishes themselves are not able to receive signals from larger angles of arrival than 3 degrees. But these 3 degrees is for the sake of the example. It could be any limit we want to include in the plot. I have my number of antennas, it is 6. And then I calculate the antenna pattern with this formula, which might look quite complicated, but it is basically the phase shifts we were doing before. We have K is the number of antenna. You can see there is a 4K in range number of antennas. And we have the phase shift for the angle of arrival, which is my antenna pattern degrees. This is how I'm computing it for many different angle of arrivals at the same time, minus the sine of my beamforming angle. And then I have the complex exponential, and I'm summing everything because that is what the beamformer does. And then I'm taking the absolute value and converting it to decibels. And I'm normalizing by the number of antennas because I want to have 0 dBs in the beamformer direction. So this formula is basically the calculation that the beamformer is doing, and this is how we can compute the beamformer antenna pattern. So let's see how that looks like. We are on the same situation as before, so both beamformers are pointing to an angle 0 degrees. And we see at 0 degrees, we get a gain of 0 decibels. That means that if a signal is coming from 0 degrees, we see it with its full power. And as we continue increasing in angle, then it decreases. That is what we saw before, until we reach something about 0.1 degrees. And at this 0.1 degrees, what we get is null. So the signal completely disappears. That is what we saw before. In fact, what I did before was something like this. I put one of the signals at 0.1 degrees, the other one at 0 degrees. And then you can see one of my beamformers, the blue one, is aiming to things which are at 0 degrees. The other one is right on top of the null, so it lets me see a different direction. Basically fills in the coverage pattern of this one. But then we can see other interesting things. For example, on the blue one, if I keep increasing my separation and I go to 0.14, more or less, I can see some signal back. So let's demonstrate that. If I put the signal on 0.1, then I cannot see it on the blue. If I continue, then it appears again, 0.3, 0.4, and it's not as strong as before, but it's back again. So we are on this part. And this is the beamformer pattern. And we can see something quite interesting. We can see that for a particular angle, which is 0.58 degrees, we again see the signal with its full amplitude, and it should have the full amplitude at this 0.57. And the reason for that is those phase shifts. So for some particular angles, because all the exponentials I have in here are periodic, then I will get a 2 pi factor, an additional 2 pi factor, and I will see exactly the same phase shifts, for example, for 0 degrees angle of arrival or for 0.57 degrees angle of arrival. This is called the synthetic beam or the main lobe of the beamformer. This is the region in which we intend to use the beamformer. These other lobes are called grating lobes. And the reason they are called grating lobes is because of diffraction gratings. If you have seen any of those diffraction experiments where you shine a beam of laser through a grating, and then you get an interference pattern on the wall, which looks somewhat like this, that's because it is actually the same thing as this. So we get a grating pattern, we get these grating lobes. If I had a dish antenna, then the gain of my dish is also going to decrease like this. So these spurious grating lobes, they are going to be of slightly less amplitude. I have a typical antenna pattern here, so that is how it usually looks like. So the main beam is going to be slightly higher power than the grating lobes. And as we go to larger angles, then this will keep it decreasing just because each of the antenna elements has a response which goes like this. Okay, what else? I will give some formulas for how to compute the distance of the grating lobes, how to compute this null, etc., and what is the effect of the number of antennas, of the separation between antennas, etc. But before that, any questions?
Do you know if you're looking at a grating lobe or a main lobe? Because I feel like if you just pointed the array at like something you didn't previously know exactly where it is, how would you know if I don't know if that question makes any sense if
The source is coming in through the main lobe or one of the other lobes.
yeah.
No, it makes a lot of sense. Your question is, for example, I'm not able to see the difference between this signal which is arriving at 5.7 and this signal which is arriving at 0 degrees, because this second signal is arriving through the main lobe, this one is arriving through the grating lobe. So that's a good question. If I have directional antenna elements, then maybe because of this. If not, then I just need additional antennas, because the reason why this happens is that because of the regularity in my array. All of the antennas are separated by a distance of d. So if I change some of the distances, then I will not get such nice and periodic and regular grating lobes. I will get more irregular grating lobes with less amplitude, and so it will be easier for me to tell what is a grating lobe and what's the main lobe. And finally, this is quite relevant for radio astronomy. If I just wait for the Earth to rotate, the apparent position of my antennas, as seen from the source, is changing. And I can keep collecting data while the Earth rotates. And this means all my distances, so all the Ds in here are going to keep changing as the Earth moves. And so I can have a virtual array with many more antennas than what I began. And the baselines I can form with these antennas keep changing over time. So I basically can collect more data so as to reduce these grating lobes. And this is called aperture synthesis. Earth rotation aperture synthesis is the proper term. So yeah, all of those techniques can help you. Other questions or comments? Okay, so some formulas. There are two quantities which are important about an array. The first one is what is the resolution, which is what is the beam width of this narrow beam, which is the main lobe, or equivalently, where is this null placed? And the formula is basically the largest separation between antennas in wavelength units, 1 divided over that. And that will give me the resolution in radians. Let's do some Python and check that formula. So in our case, we have an antenna separation which is 100. We have 6 antennas, so the maximum separation between them is 5 times 100. So 5 times 100, and then 1 divided by that is, this is known as lambda over d formula. If you have seen the lambda over d formula, this is what I'm using. I'm already writing the distance d in units of wavelengths, so that's the reason I don't have lambda on the numerator. And this is the resolution in radians, so 1 milliradian. If I want to convert to degrees, I can use NumPy, and this gives me 0.115 pretty much, which is the location in which this null happens. If we measure this more accurately, we would get 0.114, this number. So that is one formula. The other formula is the distance to the gradient lobe. This only applies in the case of a regular array, such as this one. The other formula, this lambda over d, is generic. You can use it on any array. But for this one, we need a regular array, and then basically we need the separation between each pair of antennas. So this 100 here. And then when I go to my Python, and where's Python? Here. And I do 1 divided by 100, how much is that in degrees? That is 0.572. And no coincidence that on 0.572, I have my first gradient lobe, and then the remaining are multiples, at least for small angles. Questions about this? Okay, so finally, I should say some words about interferometric imaging. This problem is two-dimensional. We are only steering our beam in one angle, but you can imagine about a two-dimensional problem where we might want to make an image over a line on the sky. And if I keep moving this beamforming angle, I could take measurements of many different places on the sky, or because this is just calculations, instead of having two different beams, which are like two different pixels on my virtual camera, I could fill everything up with many beams, and then I would have like many different pixels, and I could take an image in this way. So this is sensitive to something which is coming from this direction. Forget about annoying gradient lobes for a second. This is sensitive to things coming in from this direction, and that is what pixels for an image are. Each of them captures the power coming in from one direction. So that would be like a very cumbersome way to make an image of the sky, basically moving a beamformer or beamforming to many different places simultaneously. Because there are complex exponentials in here, in all of these formulas, in this one as well. And there is a sine function, but there is also the small angle approximation. So when the angle is small, we can replace sine of theta by just theta. So you can start to see that this looks very much like a Fourier transform. In fact, for example, in this calculation I had in here, I even have the sum of exponentials. There is a k. Forget about this sign. We can approximate it as just the thing which is inside. So this is actually a Fourier transform. And I'm not going to go into the details, but what this means is that we can do things. Where is my plot? We can do things much more efficiently by using Fourier transforms. So all these beams I wanted to put in here, by doing a Fourier transform, at once we can obtain all of them. And the whole story goes like this. We can use a correlator like we used in the previous flow graph to compute the correlations between each of the pairs of the antennas. And that will give us an output which is called visibility or complex visibility. That is not the thing we want to plot in our image, because the thing we want to plot in our image is what is on the sky. And the visibility we have obtained with the correlator is the Fourier transform of that. So we make an inverse Fourier transform, and that is how we obtain the image. By making that inverse Fourier transform, we have the same problem with gradient lobes, because we are not sampling the complete Fourier domain. We are only sampling wherever we have a pair of antennas, wherever we have a baseline. So because of this incomplete sampling, we get basically a synthetic beam pattern which has side lobes, grating lobes, or all kind of imperfections. But there are algorithms to deal with that. I don't want to mention any of them. What else should I mention about this? Yeah, the example that Steve always says about aperture synthesis and beamforming and correlation is the following. If we had a very large dish, then its angular resolution would be very fine because the angular resolution of a dish is inversely proportional to the size of the dish. And antenna arrays, in a sense, are like a very large dish which spans the whole size of the array. But it is like having this massive dish and starting to poke holes on the dish. And if we poke holes, then the antenna pattern of the dish starts having side lobes because we have removed pieces of the surface. And if we keep poking holes so as that the only thing that remains are our small dishes in the array, then we are basically at the situation in which we are with an antenna array. We have a small number of dishes which span a large area. So the angular resolution, it is very good because of the size of the large area. But the antenna pattern can have all of these grating lobes because the collecting area is not continuously covered. We are only covering some points, but because of the Earth's rotation, it is not as bad as it seems, because as the Earth rotates, we cover more and more of these gaps which are missing on the surface of the dish. Okay, so that's what I had for today, and we are also at time. Any final questions?